All right. Good morning, ladies and gentlemen. My name is Nicholas Crouch. I work at the Maths Learning Centre at the University of Adelaide. We are going to do a revision seminar for Maths 1M this time. So far, the suggestions have been techniques of integration, Newton's law of cooling, trig refresher, and maybe doing an example of induction. Sure. So I feel like some trig. So what I might do, I've grabbed the sample exam. Woohoo. And so we'll go through and have a quick look at what they've suggested, and we'll see if we can't sort of find something similar that might also be an exam question, which is not something you will have done or about to do. So we're going to have a quick flick through here until we find a bit that says, oh, yes, that's really annoying. We didn't do integration. Really? Let's see somewhere. Okay, sure. Okay, so what they've got, there is whenever there is actually a thing, where's my favorite pen? So we're going to go 1M, and we're going to go 1. Sweet. Oh, not other lecture theatres has a stool you can sit on. So, okay, I'm just going to have a quick scan. Oh, that's really painful. We should do that. All right. Why did I think this was a good idea? So we've got the integral of sine of ln of x on x. All right. So this falls under the rule of if you have no idea, it's a substitution. All right. And so because I've got a composite function, I've got a sine, well, I've got a log inside a sine. The thing that we're going to do for the substitution is the thing inside. All right. That is the most likely candidate. All right. I'm going to forget about the divide by x because I'm going to hope that disappears. All right. So, I'm going to go, let u equal ln of x. So you make a decision about what you're going to have as your substitution. And then you go, all right, first thing is differentiate the substitution. And so I'm going to get 1 on x. Sweet. Okay, now, so I'm going to do a little bit of jiggery pokery. All right, I'm going to rearrange this and go du is equal to 1 on x dx. So I'm actually going to rewrite this integral. So I'm going to have sine of ln of x 1 on x dx. All right, don't have to do that, but because I'm trying to explain what I'm doing, I want to make it quite clear that this bit here, oh, hey, there was a highlighter. Why not? Let's go crazy. So this bit here is the same as this bit here. And so that's the bit that actually tells me that I've probably got my substitution correct. All right. So this is going to become integral sine of u, and this bit's going to become my du. All right, sweet. I can do that really easily, can't I? Because the integral derivative of cosine is minus sine, so the integral of sine is minus cosine of u. And we should go plus c, because they will take, there is a mark, there is at least 1 mark in the exam for plus c. Quite literally, you forget the plus c, you lose 1 mark. Which is, I understand how freaking annoying, but also that's what's going to happen. And then I undo my substitution. All right, so minus cosine of ln of x. All right, so I'm going to point out a couple of things. Firstly, every time I pick a sub, like in my head, I will actually run through options. All right. But my brain said, oh, there's an ln, there's an on x. That's the right substitution before I could even finish reading the question. All right. So the thing that was in there, so the one from the exam paper had an ln with an on x, had the same form. That's why when I looked at it, I thought, oh, that is exactly what we should do, because we can do this. All right. But not always will it work nicely. Okay.
Did they
So-
give us the substitutions in maths 1?
Yes. But you should like,
Yeah.
well, they have in this exam. I can't, the lecturer may have said that. I don't know. I definitely didn't sit through the lectures. Back when I did lecture 1M, we didn't give you the substitution, or we didn't always give you the substitution. All right. So you had to sort of be a little bit, oh, hey, I should do that. All right. So there are things like, if I was to try something a little different, so if I was to try sort of x squared plus 3x plus 7 squared, and if I was to see this like 2x plus 3, all right, so the rule is, if there's something in the denominator, or something, then that's probably the thing that we're going to have, that we're going to let be the u. All right. So and every time, the first thing we do after we decide on the substitution, we differentiate it. Sweet. And so all of a sudden you're saying, oh, okay, I can do my du is equal to, technically I should put brackets around this so I can go that. The line, I think they call it a vinculum, the thing that separates the numerator from the denominator, is implicitly brackets around the numerator and the denominator. All right. So strictly speaking, there is sort of brackets around here. And you can see again, this bit, my numerator. So when I do my substitution, that bit's going to become du. And the bottom line is going to become u squared. I'm going to write that as u to the minus 2 du. And then, all right, so with integration, we add 1 to the power, u to the minus 1, divide by the new power. Add a constant of integration, push the page up so that you can see what I'm doing. And then back, so I wouldn't, nobody wants it like that. Minus 1 can go on top. U goes on the bottom, plus C hangs around over here. So my answer should be minus 1 on x squared plus 3x plus 7 plus C. Okay, so one of the other things is, you notice the correct answer isn't necessarily very long, all right? Used to frustrate the crap out of me when I was in first year. My friends will go, oh, we don't want to copy your answer. I'm like, why not? It's like, you haven't written enough. And I'm like, don't need to write more. So there can be a certain amount of, if you know what you're doing, you know the things that you've written are the things you need to do. This is what you need to do. The solution in the solution that I, like if I was marking this, the solution the lecturer would give me would have slightly less than that. All right. He would have done sort of that, and then possibly that. So you can get away with less, but everything you think in an exam, you write. If you are doing something correct, you write it down on your page, because the thing that's most frustrating from the point of view of the guy marking it, is people don't write enough so that we can give you marks. All right. Loving the plan? Sweet. I'm gonna pick a couple more examples. No, what else is fun? Pause momentarily. No, do want to do that. No, don't do those ones. So we don't. So this one has got integral. Thoughts, suggestions? What's that? Ah, yeah, that's a good one. Yes. What is your first thought when you do something like that? All right.
Would I want to like the
So if I do that as cosine x on sine of x, yes. So the reason I've sort of picked on that one is because of that very reason. Sometimes the first thing I have to do with an integral is a little bit of interpretation. All right. So if you play around with trig functions often enough, you go, yeah, okay, the integral of cot is whatever, right? But you have to play around, you have to be familiar with it, right? So with integrals, sometimes I like to use the phrase work it, right? You've got to rewrite it in some way. You've got to just do something that's going to help you work out what's going on. And so then my rule says the u is the denominator. U is equal to sine of x. All right. So du on dx is equal to cosine of x. And again, I'm going to go du is equal to cosine of x dx. There is no hard and fast rule about how you do this, all right? Some people will like to go, dx is equal to, so some people will say 1 on cosine of x du is equal to dx. And they will put that in so the cosine can cancel out. Not a fan, not my favorite technique. It is not wrong. So you can do whatever you want. All right. No, you can use it either. There's actually like a sort of a bit of a, there are various different ways people think about it. Doesn't actually matter as long as you do the replacing. So when I get through this, right, I'm going to rewrite my integral as, so this is just going to become, so I'm going to go 1 du on u. All right, that bit. So rewritten my thing, my denominator became my u. My top line was drawn up in replacing the dx. And so my thing is going to be like ln of u plus c. And then, okay, this is going to be ln of, I said sine of x plus c. All right. So they're not terribly tricky. So with substitution, those are actually really good. Like I would be happy putting any one of those in an exam. All right. So there are trickier things, but that's actually about the level of what I would put in the exam. So, and you can sort of, hopefully you're sort of going, yeah, okay, I think I know what to do there. The other thing to do, particularly with a substitution, is work out what the derivative is. I'm actually, there was one in the book, this one. So this was x on 1 plus x to the 4. All right. This breaks my rule. All right. So it helps to know that, what is it? Integral 1 on 1 plus x squared All right. So this is one of those exceptions where you go, oh, okay. Hashtag, I do not think you need to be able to do this. Okay. I do not think this is a thing you need to be able to do. I want to just go, this is where I go, actually, the soft signal on the top is that the u I want is actually x squared. All right. So because this is something squared, if I let u is equal to x squared, my du on dx is equal to 2x. And so I can go like a half du is equal to x dx. And so my integral becomes, so I'm going to put my half out the front. All right. So under the heading of stuff that is not impossible, if I was to tell you this and then ask you to do this, all right, not impossible for this exam, all right, it is something that I would expect you to be able, I would expect the top 20, 30% of the class to be able to do, all right. I may put this in to go, hey, let's do a little bit of a separate the wheat from the chaff. But you should be able to do this. Tan x squared, I want that to say x squared plus c. So the other thing, so I'm going to just do a bit of a quick check. So Stuart, wonderful book, has a lot of standard integrals. And so, where do you go? Yep, cool. I did just want to check that I've got that right, because every so often I get things, they're little detail, I remember a little detail wrong. So it's not impossible for them to go, here is a known integral, such as this. Here's something which is similar. Use this information with an appropriate substitution. All right. And that's where you differentiate it and go, oh, hey, x to the 4 is actually just x squared squared. So I'm going to go, I got this. This is not that bad. All right. Cool. All right. Absolute worst case scenario. They're not going to do it to you, but hey, never know. Never know. Okay. So what that's doing substitution. All right. We are going to do I wanted a little note pen. All right, substitution. Okay, that was this one. Let's pick on no, integration by parts. No. Yep, that should be the right one. Okay, so favorite thing to do with wonder if that'll work. All right. Every so often I do this and I go, this could go badly. All right. Really? I've got to. All right. Beautiful. I want to put it over there a little bit too. So, beautiful, good. Everything's working. So, with integration by parts, integration by parts is not solving an integral, it's rewriting an integral. All right. So, and I always remember product rule. Derivative with respect to x of f times g is equal to f dash g plus f g dashed. All right. And you're going, yes, sure. I remember that, Nick. That's awesome. Because everybody runs product rule for differentiation. And integration is just undoing differentiation. So I'm going to integrate through. And because I integrated the derivative, that just became f times g. And this became integral of f dashed g. And this became the integral of f g dashed. Sound like a thing? Sounds absolutely like a thing for me. Now, this does not look like what we normally have. What we normally have is something where we put one of these over the other side. So I'm going to go integral f dash g is equal to fg minus integral fg dash. So you'll notice, and you can do this yourself. There is no hard and fast rule, because I have people go, oh, shouldn't those two be the other way around? They could be. I could swap them around. That would be fine. All right. There is no hard and fast about this. This is like, it's an equation. I can play with it. All right. Now, the thing that is important, though, is particularly with this, if I go, all right, well, my f dash, I'm going to make equal to sine of x. And my g is going to be equal to cosine of x. And so I'm going to go f. So I've got to integrate that. Integral of sine is minus cosine of x. We don't worry about plus c when we're going from there to there, because that would just make my life difficult. Differentiate that, that's minus sine. So we're going to say my integral sine of x cos of x with respect to x is equal to f times g minus cos of x minus those two. Integral of minus cos of x minus times by minus sine of x. Because it's, you notice I've gone and whacked brackets around it because I'm multiplying by minus sine of x and I don't want to get confused. All right, so this is like minus cos of squared of x. There's like 1, 2, 3 minuses. So I'm going to go minus and then integral and then sine of x cos of x. Hey, what? So I've just said the integral of sine of x cos of x is equal to minus cos squared of x minus the integral of sine x cos x. That sounds like a really silly plan, but it's an equation, so that thing and that thing are the same. And my principle is I collect like terms, right? Love the plan? All right. Surely you've seen this before. Sine of x, cos of x, dx plus integral sine of x, cos of x, dx is equal to minus cosine squared x. All right. Well, that's funky and fun. But there is two of these. Two integral sine of x, cos of x, dx is equal to minus cosine squared of x. So, did we love that? I'm like, check that. That is like so awesome. So I actually right now I'm going, I don't remember ever doing that before. So this is a case where I go, I did what I thought was the right thing to do. all right? And then I just believed I was going to come to an answer, all right? Having spent the last 40 years of my life doing maths at this level, I have a fair amount of belief in my ability to come to an answer. I'm not sure it's any less than I had when I was in first year. It's just that now I actually have some backing for it. And so sometimes it's just, this is the right step to do. This is the right step to do. This is the right step to do. Oh, hey, check out what happened. Okay. So I can definitely do that sort of thing. I think that's kind of like, I'm particularly pleased with the way that worked out. So cool. So firstly, when you're doing substitution, by parts, be clear. All right. This means that if you stuff this bit up, right, and then you put it down here, the lecturer goes, he's got one of these wrong, so that's why this is wrong. All right. And you can get some credit for having done the right thing. All right. If you've just made a simple mistake with an integral or a derivative at that stage, you get credit for what you have done. All right. So, but you have to write it down before it's going to make sense. All right. So, under the heading of the next favorite thing to do with integration by parts. All right. Integral x to the cubed e to the x. So I'm keeping it to something very close to what I've seen in the exam. All right. You would not have, but I have. I've seen a lot of exams. Sure. So now, with the sine and cos, because sine, cos, they've both got this sort of cycle, a two cycle where they sort of get back, you know, modulo minus sign. I was thinking, oh, maybe I have to do it twice. All right. And so I just have to be consistent. When I've got something like a polynomial part, that tells me that I want that to be the bit that I differentiate, because that's going to simplify it. All right. So again, we're going to go integral of f dash g is equal to f g minus integral f g dash. So I'm going to make g is going to be equal to x cubed, so that g dashed is equal to 3x squared. And so that means my f dashed is equal to e to the x, and so my f is equal to e to the x. All right, did not try and make this complicated, for I don't want to make it complicated. So my integral of x cubed e to the x is equal to f times g. So it's like x cubed e to the x minus the integral 3x squared e to the x. That's a pain in the bum, because that is not complete. Okay, now, you know how I said integration by parts doesn't solve the integral, it rewrites the integral. I've rewritten my integral as something a bit simpler. A bit simpler. Not a lot simpler yet. So what I'm going to do is I'm going to take my integral and I'm going to just do x squared e to the x. And so again, my g is going to be equal to x squared. And so my g dashed is equal to 2x. And so my f dashed is equal to e to the x. And my f is equal to e to the x. Now, it's really important that we're consistent. All right. If I'm going to do integration by parts on the same thing more than once, I have to be consistent. So see how I've got like a polynomial part and an exponential part? I've been consistent about how I did it. And I made sure I'm reducing the complexity of the integral at every step. So I have to keep doing it. Otherwise, what you'll do is you'll find you did one step this way and then one step back. I want to go one step in the same direction. And so my integral of x squared e to the x with respect to x is equal to x squared e to the x minus integral of 2x e to the x with respect to x. Bottom. What say you, bottom? Sure. It's always important to know a good couple of Shakespeare quotes because Shakespeare liked to do a lot of things where you basically swearing. Integral x e to the x with respect to x. All right. So again, my g is going to be equal to x. My g dashed is equal to 1. Slick. My f dashed is equal to e to the x. And my f is equal to e to the x. And so my integral of x e to the x with respect to x is equal to x e to the x minus integral of e to the x. I'm going to go a little step further and go, that's x e to the x minus e to the x. Technically, I should put a plus there. All right. Well, so with this particular piece in mind, I can now say that my integral of x squared e to the x with respect to x is equal to x squared e to the x minus this thing, except for there's got to be a 2, because I kind of ignored the 2, because it was making my life difficult. X e to the x minus e to the x. I'm going to put the plus c out the front, right out the back. All right. I don't kind of need to incorporate it because times by minus 2 is not going to make my life any better. And so I'm going to sort of simplify this out, basically. X squared e to the x minus 2x e to the x plus 2e to the x. All right. Slick. That's awesome. But I really want to go back to integral x cubed e to the x. And so if we go back up here, I said that the thing was equal to x cubed e to the x. So x cubed e to the x. And can I get it on the same page? No, I can't. So minus 3. And then this palaver. X squared e to the x minus 2x e to the x plus 2 e to the x plus c. All right. Now, there's actually a trick, right? So this is fairly horrible. And this is where my favorite t-shirt comes in. Factorization is your friend, all right? So factorization is that friend who, when you have a bit too much drink, suddenly you find your hair's tied back and there's a bucket for you to chunder into, right? Factorization is the sort of friend who goes, yeah, she looks good, but you don't want to go there, mate. Let's move on, right? So factorization is always looking out for you, all right? This is the thing I want you to walk away with. Factorization, looking out for you like you wouldn't believe. If I take e to the x, see all these terms have e to the x in them. They kind of suck a little bit, but they all have e to the x. So I'm going to go x cubed, and then I'm going to go minus 3x squared, minus 3 times minus 2 is going to get me plus 6x minus 6 plus c. See how much prettier that looks? All right. So there is, no, I don't think you do talk about reduction formula, do you? So this is an example of, I could have gone right up the very start. I could have said x to the n. And then I could have written my integral of x to the n e to the x in terms of x to the n and x to the n minus 1. And that would have made it one step simpler. And then I could have just applied that rule over and over again. So there are a couple of sort of standard sort of processes for doing integration by parts. And one of those is to create a rule that helps you simplify it one step at a time. And this one, I've seen them use x squared in an exam. You had to do integration by parts twice. All right. it is not uncommon to have to do integration by parts twice. But also noticing factorizations, so much better, so much easier, right? Simpler, prettier, it's going to save you time, money, and effort, all right? So how do we feel about integration by substitution? By parts. So things I want you to remember about by parts is sometimes there's working after I've done my integration by parts to notice what what it's telling you. All right. So notice that I may have rewritten the integral as itself. All right. And so bring them together, do like my standard algebra, treat it as just like a single algebraic unit, bring it together, combine them. Oh, I've got some multiple of the thing I want. Let's just divide by that multiple. Or sometimes I have to do many steps. So sometimes if I see an exponential and a trig, I go, probably I have to do that twice before I get the original integral back. Put it together, got myself an answer. All right. So that can happen as well. So sometimes if I see a trig function in there, I go, maybe I have to do it by twice. I half expected to have to do it by twice, to be honest. For that first example, this one, I knew exactly what was going to happen. All right. Because I've seen it before. But, you know, you see that polynomial, you go, I don't know what that integral is, but I can simplify it. I can simplify it again. If in the exam you're running out of time and you just did one lot of that simplification, and you go, I could do this a couple more times to get to the end, right? That would get you a lot of credit. All right. You know, there's doing it right the first time, 2 or 3 marks out of however many marks. The next step is probably only 1 additional mark. So if you're sort of pressed for time, that can be a trick to help you reduce the complexity of the problem. Okay. So we said Newton's law of cooling, didn't we? Where did I put that page? You know what we should do? We should, I'm going to go, where did we say Newton's law of cooling here? That's right up the start. Come on. Newton's law of cooling, 65. Bit too far. Newton's law of cooling. Woohoo. Okay, so where was I making notes? Okay, 1M5. Okay, so if we go back to what the differential equation says, the rate at which the temperature changes is proportional to or equal to a constant times the difference between the object's temperature and the surrounding. All right. So this could be, I have taken, so playing around with, every so often I play around with stuff, right? I do cool things. I need to swap the thing I'm sharing. Stop that share. Hey, and camera. Sweet. So I found lead on the road. They use lead to balance car tires. I went through, I picked it up, and I thought, you know what? You can make models with your chunks of lead, right? So I can't remember what temperature lead melts at. I think it's about 200 mid 200s. You guys know? No, not off the top of your head. Sure. That's what Google's for, right? So what I did is I literally got an old kitchen pot, put it on the stove, melted my lid, got my little cast that I've made myself a little thing. So let's pretend. Let's go. So we need to go, hey, so for us to work out what we do, we need to read the information from the question, all right? So no, we don't want to do Fahrenheit. No. We got a nice, we'd like a nice question. Oh. I should have a look at that before we go too much further. There we go. We should do something more applicable to today. Well, this time of year, because Christmas pageant is on Saturday. All right, we're all excited about the Christmas pageant, aren't you? You guys look like you're going to be there. You're going to be staking out your spot 8 o'clock in the morning. There. Sure. Roast turkey. Roast turkey is taken out of the oven. I'm going to. I'm going to look at question 13. So roast turkey taken from the oven when the temperature has reached 185 degrees Fahrenheit and is placed in a table in a room where the temperature is 75 degrees Fahrenheit. If the temperature of the turkey is 100 after half an hour, what is the temperature after 45 minutes? Okay. And when will the turkey cool to 100 degrees Fahrenheit? All right. So what first thing to do when you get a question like this? All right. So we've got this this thing here. I forgot to get the important part about this. So actually no, I'll go through and do that. So first thing we're going to go T0. I'm going to treat T as a function of time, and we are saying that the temperature of the turkey is 185 degrees Fahrenheit. All right. Sounds like a terrible plan. We are saying the ambient temperature is equal to 75 degrees Fahrenheit. This is what you get if you use an American book. And half an hour. So we're going to use T in hours. And so T of a half is equal to 150 degrees Fahrenheit. I feel like the turkey is going to take a while. Okay. Let's see which I need to be talking about that. Sweet. There, I pushed that. Okay, so first thing we really should do, right? I'm sure your lecturer has done this, is take this differential equation. So dt on dt is equal to k t minus t naught, ta. And we rewrite it as 1 on t minus ta dt is equal to k dt. All right, love the plan. And then we're going to go, I can integrate both sides. Make sure I use the right t's, because that is one of those things. All right, I can do this. So this one is going to leave me with ln of t minus ta. And this one is going to get me k times t plus c. Okay. Excuse me. The reason I've written it that way, so I've only added one constant of integration, but if you imagine I'd added two, but then I collected them together because they are quote unquote like terms. All right, so then I'm going to take exponential of both sides. So I'm going to get t minus ta is equal to e to the k t plus c. And we are going to write that as e to the k t times e to the c. And so it's kind of tradition to go, well, so I'm going to go t as a function of t is equal to ta plus e to the k t times, I'm going to call that e to the c some other number. All right, e to the c is a constant, e to the c is a constant. I'm going to call it that. And then I'm going to go, but I know something. T of 0 is equal to 185. But it's also equal to, TA I said was 75, plus a times e to the k times 0. That number is 1. This is like 75 plus a. And so therefore, a is equal to 110. A was always, you kind of know this because you've done this enough times. I've not put that up the page far enough, have I? So A is always going to be that difference between the ambient and the initial temperature. All right. We know that. And so we're saying our T of T is equal to 75 plus 110 e to the k t. We are still short of one of these constants. All right. So we're going to use the next piece of information we were given. All right. T of a half is equal to 75 plus 110 e to the k on 2. T is a half, k on 2. But also, that is equal to 150. And so I'm going to go put my 75 over here. So I have 110 e to the k on 2 is equal to 150 minus 75 is 75. And so e to the k on 2, okay, come on, is equal to 75 on 110. I reckon I could simplify that down to go that if I divide by 5, that should be like 15 on 22. That's a horrible looking number. And I don't care. I'm actually going to work with this number as it is, right? So I'm not going to try and go, so k on 2 is equal to ln of 15 minus ln of 22. So k is equal to 2 ln of 15 minus 2 ln of 22. All right. This is where it's going to cause me some problems, but I'm going to work with it anyway. So this is kind of like, I've got this number. Maybe I was better off writing that as 2 ln of 15 on 22. So my log laws allow me to either do this or this. I don't care which one we do. I sort of thought it would be easier like that, but maybe it's going to be better like this because I'm going to be able to go T of T is equal to 75 plus 100, 110 e to the 2 ln 15 on 22 t. Okay, so I want to work out where that's equal to question said, where question said, question said, all right, question said, when does the turkey reach 100 degrees Celsius, Fahrenheit, 100 degrees. Okay, so we're going to do the same thing. We're going to make this equal to 100, all right? And so we're going to get sort of 110 e to the 2 ln 15 on 22 is equal to 25. All right, that's going to annoy me, but let's go. Okay. So I've got 110 e to the 2 ln 15 on 22 times by, whoops, t. All right, t is equal to 25. And so e to the 2 ln 15 on 22 t is equal to 25 on 110. Bleh. Nobody is loving that. Okay. Now, okay, the thing I have to do now is natural log of both sides. So this bit, natural log, because it's e to the ln, I'm just getting the power. 15 on 22 times by t is equal to, I wanted to write and reduce that down to that. So again, factorized, cancelled out common factors, made my life simpler. Don't have to do it. I play with numbers a lot, so I'm actually quite good at doing it. ln of 5 on 22. Now, you might be going, but why would you want to do it that way, Nick? All right, because. So I'm going to go t is equal to ln of 5 on 22 on 2 ln of 15 on 22. I feel like that's a bit of a pain, but we're going to work with it. Now, what I would actually do, if I was sitting in the office doing this, we're going to one of these. Where have you got it? I've got Zoom open, Excel open here somewhere. Ah, there it is. Come on. So literally what I would do is I would go, all right, well, Excel does the work for me. So I'm going to go 15 on 22 is that number. Do I need to there we go, beautiful. And I want to go view 100%. No, I want to zoom. We're going to make this 200%. Okay, beautiful. Bigger numbers. So all I've done is just done natural log. So I've done one part of the calculation, that's the denominator. Let's do the numerator, equal ln of 5 divided by 22. All right, that's that number. And so the t that I'm looking for is going to be equal to that number divided by, I'm going to use brackets, 2 times that number. Got that the right way around. Wee. All right. 1.934. All right. So if I really wanted to go equal to that number times by 60, and so you go and see that's like 1 hour and 56 minutes, or 4 minutes short of 2 hours. So this is saying that the inside of my turkey, if I got my inside of my turkey cooked, even if it's been sitting out for 2 hours, the inside is still the outside is probably not, but the inside definitely is. All right, okay. So do we want to, so when we're talking about Newton's law of cooling, I think the key parts, I don't know that they will expect you to do, let's change this around. Let's get rid of that. And then we go, come on, no, camera again. So they won't necessarily expect you to do the differentiation, solve the differential equation. You can actually just jump to a form like the form like this down, whoops, just off the page. Beautiful, Nick. Something like this. All right. Okay. We've talked about it. You've gone through it in class. You've done examples. Unless they actually say, hey, we want you to do this, you can jump straight down to here, all right? Where you've got your unknowns. You've got your A, which is associated with that difference between initial temperature and ambient temperature, and then you're using the extra information. The thing that possibly people don't do often enough that is really helpful is actually writing out the information you're given in a clear, concise way that matches the way you're going to talk about it through the problem. So that's actually, this bit is probably the pro tip. I did a lot of, I'm very bad at remembering formula. And so in my exam, I did a lot of, when I was in first year, did a lot of doing this, where I actually did do this is the formula I'm supposed to use. It allows me to, I can know how to get to the formula rather than remembering the formula itself. Questions? Comments? Sweet. All right. Okay, do we want to do another one or do you want to just keep moving? With one of the things I noticed in that area, in this section of the textbook, was questions about decay, exponential decay. Let's just go to the notes quickly. Go to the notes. Okay. There are, so separable differential equations. It's important to remember when you talk about differential equations that you're not going to get something complicated. All right. They are going to keep it reasonably simple. Okay. So the worst thing I've seen them do when they're doing something like this is a differential equation that looked like right. Yeah. That not terrible. Okay. Because actually possibly that is terrible, but we're going to ignore that detail. All right. Because the key part about this is, like I said, factorization. All right. There are times when I go, oh, I've got that. I've done a silly thing. All right. So because I've got dy on dx is equal to x squared y minus y cubed, then I'm going to be able to write that as 1 on y minus y cubed. Dy is equal to x squared dx. At this point in time, I'm going to go, oh, that's terrible. All right. The technique needed to solve this integral is a bit complicated. All right. So, you know what I can do? I'm going to not, I'm not going to go through and solve it because I can. All right. You guys are not supposed to know how to do that yet. All right. I'm not sure if you learn in 1A or 1B, which are not 1A and 1B next semester or next year. But it goes beyond what you're supposed to know how to do at this point in time. So I'm not going to do that. But I did want to point out this trick where, same as I was saying with the integrals, when I'm doing a substitution, I have to do a little bit of work. That remembering that I can do a couple of steps of simplification or reorganizing to make it fit the form that I want is important. All right. So they have done something similar to that. If I was to write this as sort of dx on dy is equal to x squared y minus x squared y cubed. Then what that would mean is I would have 1 on x squared dx is equal to y minus y cubed dy. And then I could do something about it, right? So when I slip in my integral sign, and so this is x to the minus 2, so it becomes minus 1 on x is equal to, integral of that is like y squared on 2 minus y4 on 4 at a constant of integration. All right. So can do that. All right. And there's absolutely nothing wrong with doing it that way. Just from the point of view of trying to do this sort of thing, that would be a way of solving that problem. So yeah, the swapping around the role of x and y, I only did that so that I could reuse the same problem. Do make sure you read what the question says. All right. Are we cool? Loving the plan? Let's go on to what was next on my list. Oh, trig refresher. Trig. Okie dokie do. So, if we grab Mr. Yieldy sample exam here. All right. Ooh. So, horrible question. So there was something like sec x is equal to 2. So, do I want 2? Yeah, I'm going to pretend that 2 is going to be all right. 2 is going to be all right. Okay, so what is my plan? Right, so this one here I need a sine and a cos. This is 1 on cos. Maybe I should start there. 1 on cos of x is equal to 2. And that very nicely leads me to cos of x. I didn't want 2 because it's going to be a half. All right. All right. So if I have cos of x is equal to half, then I'm going to go cos squared theta plus sine squared theta is equal to 1. Okay, I'm going to add a little bound for this, all right? Because when I do this, I'm going to get 2 options for sine. So I'm going to go, so then I'm going to have myself a half squared plus sine of x squared is equal to 1. So sine of x squared is equal to 1 minus 1 on 4. Half squared is just 1 on 4. And that's just like 3 on 4. And so sine of x is equal to square root 3 on 4. I really should have a plus or minus here. Now, this bit here. All right. Whenever I'm doing trig things, you see me do this, a little bit of a diagram. And we go minus pi. So I'm going minus pi on 2. So I'm in the 4th quadrant. We needed to have cosine as negative. So we're gonna adjust that. Sure. Third quadrant, sorry, third quadrant. And third quadrant is where both sine and cos are negative. All right, sweet. So strictly speaking, this is minus square root 3 on 4. I'm going to go minus root 3 on 2. I like that better. And then my tan of x is equal to sine of x on cosine of x, which is equal to minus root 3 on 2 on minus 1 on 2. When I'm dividing by a fraction, so minus 3 on 2, I multiply by the reciprocal. 2 on minus 1. My 2's cancel, and strictly speaking, these minus signs cancel. And so I'm left with root 3. Sweet. So there is trig identities that are going to make my life easy. All right. Lots and lots of trig identities. There is so many trig identities that it can be almost impossible to work out what you need to remember. Okay. This one, the cos squared plus sine squared circle identity, because it's literally describing the unit circle, that is a must. All right. So there are basically one for each of the other ones that I sort of hold on to fairly tightly. All right. So there is cos of theta is equal to cos of minus theta. All right. Very useful. Correspondingly, sine of theta is equal to sine of pi minus theta. All right. Way more useful than you realize. Okay. Actually, there is the last one I tend to like, the one about tan that I remember is actually if I take cos squared theta plus sine squared theta is equal to 1, but then I divide everything by cos squared theta. And so that is 1, and that is plus tan squared. We are just off the page, aren't we? Tan squared theta is equal to sec squared theta. All right. So I tend not to remember a lot, but I tend to remember how things work. Okay. So what I find interesting in this exam, yep, sure. So in a similar way to this one is doing solve certain, here's an exact value, use the thing we know about these functions to get another value. And it's almost always using the sec squared, what those other functions are, the sec, the cosec, and the tan, cot. Just interpret, use the formula. Sec squared is equal to 1 on cosine. All right, well, I'm sorry, sec x is 1 on cosine of x. I'm just going to go write that down. I'm going to then interpret it, all right? So it's take the information and do a step of interpretation, all right? It's like translating your math into sort of language, all right? And so you go, oh, okay, I do the direct translation. So particularly when you're starting to learn a new language, there is the direct translation. That word means this thing, that word means this thing, that word means this thing. That doesn't make sense when I read it, but I put it together and I go, okay, that means, it's like translate the words, read it again, write down what it actually means. So math's a similar sort of thing. Direct translation, oh, it actually really means this. Okay, so I can actually go through and work out what's happening. So the next sort of thing they have is if I go like sine of, I don't know, let's say 3x plus pi on 3 is equal to, I don't know, what's a good number for it to be equal to? I'm going to go with 1. 1. 1 makes my life easy. All right, now. Okay, I've given myself a 2 pi range. That 3, sine 3x. What is that doing to my life? So that number, because it's in front of the x, is going to modify the period. All right. And actually, a way to interpret that, so the period of sine is traditionally 2 pi. That 3 tells me that I'm going to get 3 periods in my traditional 2 pi region. All right. All right. So it actually means that the period of this function is 2 pi divided by 3. So you notice that reciprocal relationship between that value and the period. All right. So a lot of people make that mistake of going, makes the period sort of 3 times as long, makes it a third. All right. So because of that, I noticed that the region I've been given is 2 pi. And so normally with a sine thing, I'd expect sort of, because it's equal to 1, that's the maximum value of sine. I'm going, okay, I'm going to expect 1 value where it's equal to that. Because there's 3 periods, I'm expecting 3 answers. Okay, so I need to be a little bit, okay. I need to do more than just to go, okay. So the first step is to do arc sine of both sides. So arc sine of 3x plus pi on 3 is equal to arc sine of 1. That number is going to be pi on 2, but I'm going to go plus some multiple of 2 pi, all right? So we get used to this. I'm going to add some multiple of the standard period, and I want to do it at this stage because then I'm saying 3x plus pi on 3 is equal to pi on 2 plus k lots of 2 pi. All right, so my 3x is equal to pi on 2 minus pi on 3 plus k lots of 2 pi. I really should say k is in the integers. This is a way of saying that the value of k is an integer. So it's just saying it's a member of the set of integers. And so x is equal to 1/3. And so pi on 2 minus pi on 3 is pi on 6. All right, so I've got to apply that 1/3 to both the first thing, but also the K2 pi. All right, so it's going to be pi on 18 plus K lots of 2 pi on 3. This is where I swear slightly because I'd really like to put all the answers on the page. So if I draw draw a bit of a number line to where these things are, let's just go to the next page. Next page. I want to put, I'm going to bring that down a little bit and go 0 minus pi, pi. This one, quite close to 0. So when I add 2 pi to it, so this is 2 pi on 3, going to be close to pi, but it's still going to be less than pi. And so when I take off 1, it's going to be there. I suspect if I take off 2, that's getting me my 3 solutions. I possibly will check, but just going. So I'm going to go x is equal to pi on 18. Pi on 18 plus 2 pi on 3. And pi on 18 minus 2 pi on 3. So I've chosen values near there to work out what they are. So this would work out to be 13 pi on 18, and this would work out to be minus 11 pi on 18. Because 2 pi on 3, so 2 pi on 3 is equal to 12 pi on 18. So create the common denominator for my values. That's all I've done, but I've realized I've just done it in my head, so that's not very helpful for you. And I've got my values. All right. And I'm going, all right, they're my 3 answers. And I kind of can go, all right, if I added another 12 pi on 18 here, that would be 25 on 18. That's more than 1. If I took another 12, that would be minus 23 on 18. That's less than minus 1. It's outside the range. So I've made sure I've done a little bit of checking to make sure I've actually got the values that I want to have. Okay, loving the plan. Sweet. Okay. Now, there is a little bit of all right. Okay. All right. So A multiplies the amplitude. So it is the amplitude. This is like equal to a half. So the amplitude isn't the distance between the maximum and the minimum, it's half of that distance, all right? So it's the variation, the maximum variation from the midline, okay? So B. Okay. I'm going to say Okay, all right. So each of these values has this thing's just there we go. So each of these has their value, and it can help me work out what's going on. All right. So, so maybe what we should do is we should pick on something a little different. So we should go, I don't know, 3 cosine. I'm just going to say 2x plus pi on 2 minus 1. Okay. So when we come to doing something like this, what I would do, all right, so my midline's at -1. And my amplitude is going to be 3. So what I'm going to do is I'm going to put okay. So my plan is to just sort of go how far do I want to go, do you reckon? If I make that pi, and then I go another one, I can go 2 pi, and then I can go out a little bit this way. So my plan is always to put down a little bit of information about stuff. So I've set it up so I've got my value, initial value put in. Next trick, if x is equal to 0. If x is equal to 0, then I've got cos of pi on 2, and cos of pi on 2 is, and cos of pi on 2 is 0. So this bit is 0, so I'm at -1. So what I'm going to do is I'm going to go, hey, I'm here. Now, I've broken my thing into pi on 4. So if I go x is equal to pi on 4, I'm going to go, that would be 2 lots of pi on 4, which is pi on 2 plus pi on 2. And so that's actually going to be where, so cos of pi is -1. So this is pi on 2, this is pi on 2, cos of pi. And because this is -1, so it's -3, -1, -4. And so I've got my point here. But then, so I've had a look at my period. Stuffed up. Deep breath. Want that to go here. But be very, very careful. What did I just do? So one of the things that happens a lot is I make mistakes a lot. And I've been doing it since I was a very small kid. And so I'm very good at going, hey, let's check what I've done. And so, you know how I said this 2 modifies the period. So there should be 2 periods in a regular 2 pi thing. That means the period is 1. And I was going, I put this value wrong. Because I was drawing a standard standard cosine curve. I forgot to halve my period. So I did a bit of a check and gone, oh, okay. Because once I've got 2 points, I really should be able to just sort of fill it out. So this point should actually be on the axis here. And the next one should be up at the maximum value here. And then we're back down here. So my graph, I might actually try and do it in this color. So what I would do, so I'm suggesting we go that way, that way, that way, that way. And so then, so I'm going to just, And so all I'm going to try and do is draw a nice sort of sinusoidal wave between these points here, all right? So I tend to break my, all right, sweet. That is what it should look like. Now, reality check. All right, so things I'm going to check now. Midline's at -1. Maximum should be amplitude plus a midline, so it should be at 2, tick. Minimum should be at -4, tick. I've incorporated that for a 2 pi period, 2 pi region, there should be 2 full periods. So between here and here is 1 period, and here is a second period. So a full period for this function, I'm just going to do this here, is this bit here. That's 1 full period, because you can see it's got a peak, a put off, it started at midline, it's returned to the midline. So could I write that function more simply? This is one of those funky things. What do you see about that? Like if I was to show you that graph, so the thing we know about sine and cos is they're basically horizontal translations of each other. Yeah? And so this, because it starts at the midline, because of this horizontal translation, what it's done is it's pulled cosine back by pi on 2. But then half the period bring. So this could be written as 3. Because it's at the midline, I'm going to use a sine, 2x, and then -1. So these two are equivalent. Forgot a little thing. Yep, that works. Okay, so because also it's going the wrong way, I'm going to use the phrase the wrong way out of our midline point at 0. I need a minus sign in front of my amplitude. All right. So tricks people make mistakes with. Amplitude is a positive number. All right. So if I have a minus in front of my 3, when I ask about the amplitude, I go, that number is -3, but the amplitude is 3. It's a distance. Okay. Period is also a distance. All right. So period is equal to 2 pi divided by 2 is equal to pi. Okay, what else could happen? That's that. Oh, derivative. Okay, sure. So that's the sort of process we think about it. So what else have we got? There's there is one more slightly annoying thing. There we go. So the last thing that you sometimes see no, what do I want to do? What is the thing? I didn't do it in this exam. Which is a good thing. But okay. Let's see. I'm just going to sort of talk about rewriting this particular expression, all right? So this is where these things will come up in the solution to these to some sort of problems, and I'm basically going, I can't think of a nice problem that will make it come up quickly, so I'm going to ignore the details. But sometimes you can be faced with a sign of an arc cos sort of thing, and what that means is I want to rewrite sine in terms of cosine. So I'm going to go back to the standard circle identity. And then I'm going to go, well, sine squared theta is equal to 1 minus cosine squared theta. And so sine of theta is equal to square root 1 minus cosine squared theta. I should have a plus or minus here. So my sine of arc cos of x is equal to plus or minus square root 1 minus cos squared of arc cos of x. Now I want to do it that way because cos of arc cos is just x, isn't it? And so this thing has an expression. I know what they do. They usually do a question that says like, show that, and then sine of arc cos of x is equal to square root of 1 minus x squared. X in x would be in, I don't know, 0 to pi, something like that. Okay, by knowing where x is, I know that sine has got to be positive, and so that should be right. So that can be right. Yeah, sure, whatever. I'd need to. Yeah, anyway, I'm going to something like, they will say something like that, which will allow you to work out what it is. That is not right. I'm going to ignore that for the moment and just move on. All right. The last thing the sample exam had was derivatives. Derivatives of trig functions. So what the hell? Let's do this. If I do the derivative with respect to x, start with something simple, tan x. The reason I'm going to do this is I'm actually going to do this as the derivative with respect to x of sine x on cos of x. All right, and we know the derivative with respect to x of f divided by g. My quotient rule is equal to derivative of the top line times the bottom line minus top line times the derivative of the bottom line on bottom line squared. The negative, the negative travels with the derivative of the denominator, okay? Negative travels with the derivative of the denominator. So for our function, derivative with respect to x of tan of x, derivative of the numerator is cos of x times the denominator, cos of x minus numerator, sine of x times by the derivative of the denominator minus sine of x, all on denominator squared, cos squared x. All right, let's simplify that a little bit, and that becomes cos squared of x, and there's a minus and a minus, that becomes a plus sine squared of x, cos squared of x, which is equal, that is 1. Cos squared of x. So we notice that this simplifies down to 1, and so this is where we get sec squared of x. All right, we should know that derivative, but going through, all right, you can do that whole process. So, yeah, Nothing up my sleeve. Hey presto. So if I do the derivative with respect to x of, I'm going to say 10x, 10 of x of, all right. So this is kind of weird. All right. So I've got a composition of functions now. And so that means chain rule. So I'm going to do the derivative. Since I've just worked out what the derivative of tan is, I'm just going to use sec of thing inside the brackets, x plus sine of x. But then I've got to times by the derivative of the thing inside the brackets. And because it's a sum, I've got to remember to put that product in brackets, because the derivative of x is just 1, and the derivative of sine is cos of x. All right. Beautiful. A little bit too easy? Of course it is. So this is one of those things where we go, okay, so when you see differentiation in an exam, you should be thinking, right, give me marks, right? Because there is nice rules. You should know the rules by now, and it's just a matter of following them consistently. Okay. So can't do much more than say, hey, do that. Okay. So got those things. Are we happy with our trig refresher? Is there anything we think we might have missed? About the only thing with trigs is, remember, you can draw a triangle. All right. So if I say sine of x is equal to 1 on 4, all right, I can do that. All right. And so therefore I can go, I can work out that length there, which is like square root of 15. Sick, right? Did my thing, that squared minus that squared gave me that number. Sweet. And so therefore I can do like cos of x is equal to cos of x is equal to adjacent on hypotenuse, root 15 on 4. And 10 of x would be opposite on adjacent, 1 on root 15. All right. So I can draw a diagram. So if I'm given a sine value, this is the same as using that circle identity to work out what cosine is. All right. This gets you the absolute value. You need to then consider which quadrant the value is to work out whether it should be positive or negative. Okay. So you can always do that. There was a thing I might yeah, no, I think I'll let that go. I think that's fraught with danger trying to do something like that. Okay, proof by induction. All right. All right. The plan is always show the base case, show the next case. Let's do something that might suck, but what the hell? Hey, we can do this. I'm trying to think of something. So there is a couple of things. So if I go sum I squared, I is equal to 1 to n, that is equal to n plus 1, 2n plus 1, 6. All right. All right. I know that to be true. All right. So when it comes to induction, all right, we're gonna kind of believe that we're gonna get it right. All right. I know I keep saying this, but there is know the algebraic steps, believe we're gonna get it right. And so let's go shopping. Just before I go too far, I just wondered if he's got some. No. No. Okay, sure. Okay. So when I was taught to do this in year 12, we're actually told to go let P of n be the proposition. All right, so if we define it as a proposition that is dependent on n, all right, then we can go P1, the first case, would be saying sum of I is equal to 1 to 1 of I squared is equal to 1 times 1 plus 1 times 2 times 1 plus 1 on 6. This bit is 1 squared, which is equal to 1. And this is equal to 1 times 2 times 3 on 6, which is equal to 1. P1 is true. All right. So the thing about induction, a little bit tedious because I'm going to do the same things over and over again. All right. I'm going to write a lot of stuff. So we're going to go suppose PK is true. And then I'm going to go, feels like I'm going to be selling myself short, but I'm going to go I've said PK is true, and then I've written out what that means, what exactly that statement is. And it's a supposition, so it's an assumption. We could replace that by the word assume. We maybe should replace it by the word assume. Now, this is where you have to look at the thing you're being asked to do, okay? But somehow I need to consider the next case. So I'm going to start by going I squared, I is equal to 1k plus 1. All right. That is very clearly from our understandings of what we have. Sum I is equal to 1 to k, I squared, plus k plus 1 squared. All right. Kind of a standard thing where I've gone, what's the next thing? I'm not assuming the next thing. I'm not writing out the next thing. I'm taking one part of it, and then I'm going to use the assumption. I've set it up so I can use the thing that I've just assumed. Okay, so I'm now going to go, well, that and that are the same thing. So I'm going to write this. So I'm going to go k plus 1, 2k plus 1 on 6 plus k plus 1 squared. You know what I'm going to do? I'm going to go 6 here and 6 here so that I can put them over a common denominator. That sounds like a great plan. People playing at home, that is a great plan. All right, anytime you have fractions, create a common denominator, add numerators. Hopefully it's going to help. All right, so I want to be down about there. And so this thing here is going to be like k plus 1, 2k plus 1 plus 6k plus 1 squared on 6. Now, I am pretty sure I tried to explain to you how cool factorization is. How factorization is the friend you want to have as your wingman. All right, factorization is getting you out of trouble. So, we are going to go k plus 1. There's a k plus 1 here, and there's 2 of them here. So I'm going to go k, 2k plus 1, 6k plus 1 on 6. Loving the plan so far. All right, so I've got my k plus 1 here. This bit here is going to get me 2k squared plus k plus 6k plus 6, all on 6. And I'm going to go k plus 1, 2k squared plus 7k plus 6, all on 6. This is going to be equal to, all right, so I've got my k plus 1. If I go 2k and k, and I have a 3 here maybe, and a 2 here, hey, that's going to factorize like that. I'm going to do that. That's a 2. 2k plus 3 on 6. Now I'm going to get a little bit pedantic here and go, this is k plus 1. This is k plus 1 plus 1. And this is 2 by k plus 1 plus 1 on 6. All right. You might be going, but why, Nick? All right. But if we go back to what we were trying to prove up here, we're trying to prove sort of, I want to replace k by k plus 1. That's exactly what I've done. That I've replaced sort of k by k plus 1, k by k plus 1, k by k plus 1. And so this says p k plus 1 is true if pk is true. All right. Sweet. You're all happy with that plan? There is nothing remotely challenging about that, hopefully. So, now we'd do something like as p1 is true and pk plus 1 is true if pk is true by the sweet. So strictly speaking, we should write that out in full because we're saying, I've shown the base case, I've shown the inductive hypothesis, I've shown the inductive step, and that means I can now apply the principle of mathematical induction to say this is true for all n, all right? There is lots, so you don't get, they don't make it too hard for you. Showing divisibility is one of the hardest things they can do. But I don't have an example I can think of off the top of my head where I show show the divisibility thing. The plan is like, if you think about it, right? If you set up the machinery, induction question, 3, 4 marks, right? If you do everything but the inductive step, all right, you go, ooh, don't know what to do there, right? If you do everything, you've still got half the marks for that question, all right? So you can not know how to do it, but still do everything around it. And you are going to follow the rules, right? You're going to go, oh, well, I need this thing to do this. I will take that I will look at the I will consider 1/2 of the next equation I need to show. I will try and manipulate it so I can use the thing I've already assumed. And then I'm going to hope that inspiration strikes and I end up with something that's going to happen, that's going to work out for me. Okay. Are you good? I'm going to stop there for the moment, I think. I forgot to do that, didn't I? I think it was. Questions, comments? Please stop now. So it's important for you to remember Math Learning Centre is open 10 till 4 this week. From next week we go 1 till 4. I don't know when your exam is, but I have the feeling it's reasonably soon in the exam period, isn't it? Or is it late? A week up, so it's miles away. Hashtag we don't know when the exam is because they don't tell me when the exam is. I'm relying on other people's. Look up the exam time for your damn self. Make sure you check the exam time. So basically next week until we stop working, Math Learning Centre is open 1 till 4. All right, so only the 3 hours in the afternoon. If you can't make that and want to talk to us, send us emails. Look at our website, there is emails. There is an email address, there's a phone number. So if you absolutely need to absolutely want to talk to us, but can't make our slightly reduced hours, we're happy to do that. But honestly, it's just not worth our time sitting in the drop-in center because no one will be coming. All right, cool. Thank you very much for your attention, comments. I really appreciate people actually being on the ball and helping me not stuff up. All the revision seminars that we've done so far are available on the Maths Learning Centre website. So you can look at those. This one will be up maybe even today, possibly tomorrow. Going to say good luck to everyone for the exam. Come and talk to us in the Maths Learning Centre, and thank you for coming. I should have done that so you can see me. See me. Stop recording.